Okay, as you see in this slide show, today I'm gonna explain about the STT MNAM, which one I already mentioned many times, and this is a very important technology in modern spintronics. And especially the STT make many kind of new phenomena, and one of the most important thing is current-induced magnetization switching. And today, we're going to have many mathematical expressions, so please pay your attention, and otherwise you're going to lose your way. So, okay. Yeah, this slide I already showed you when I explained about the field-driven MNAM, in other words, conventional MNAM. And this field-driven MNAM, they have many problems, and actually there are 3 problems. So that's why industry gave up to develop this field-driven MNAM. And one is the scalability, and the other one is selectivity, and the other one is small TMR ratio. And I already mentioned that with the MGO TMR, we got a very large TMR signal, 300%, so it's good enough. So the third problem, the low signal, may be solved. And the other problem, the scalability and the selectivity. The scalability means when you link down the size of the device, the energy should be decreased. But in a field-driven MNAM, when we decrease the cell size, the required switching current is getting larger. So that means if you make a smaller devices, we need more energy. So it's not good devices. But with this STT technology, the required current or required energy is scaled with the dimension of the magnetic cell. So this is good news. If you make a small cells, small memory cells, you need small energy. And also, in a field-driven MNAM, we have a problem of selectivity. If you want switching some specific cells, you should be switching that specific cells, and the other cell should be not switched. But in a field-driven MNAM, there are many malfunctions because of the Western field of the current line is affect to all cells near the their path. But in a STT, we're gonna explain the current is passing through this cell the cell itself. So there is no way they disturb the next cells. So it's 100% selectivity technology. So as I said, there are many problems: the selectivity and the scalability, and not enough signal. And this one is solved by the MGO barrier, and this STT technology can solve these 2 problems also. So with this STT MNAM, many people called this is STT MNAM or just STT RAM or spin RAM. There are many similar names, but all they means the similar one. In this table, there are requirements of the good memories. And this green color implies it's good for this performance. The red one is bad. So for example, in a DRAM, they looks quite good, but they require the refresh and this volatile memory, so data cannot be retained. In other memory, for example, flash memory, yeah, they store the information good, but other part is all red because they require the high power in a read write, and the number of rewrite is limited, and the access and the writing speed is quite slow. compared to this other technology, they are all single digit in writing and reading, but they have a very large value. So the flash memory itself is very slow memory actually. But your personal feeling, maybe flash memory is not so slow because when you compare to the hard disk drive, it's fast enough. But if you compare other memory, it's very slow memory. And also other problem of the flash memory is number of rewrite. They cannot rewrite forever. For example, in other memory, the rewritable is 10 to 15 something, but in this flash memory, they have only 10,000 or 100,000 times. After this kind of rewrite, they cannot be, there are possible errors. So to overcome this problem, the flash memory using some special technique. For example, if this is the full area of the memory in a hard disk drive, for example, if you write some file here, and if you rewrite this file with a small modification, they writing here again, many times in the same place. But in a flash memory, if you save a single file, and if you modified this file, they save in other area, because they want to use the full area of the memory to reduce the number of rewrite. So they require other new technology. Okay, and let's focus on the STM. Yeah, they are non-volatile, and cell size is a little bit larger compared to other ones. That's the one problem. And the read-write time is good enough, and almost infinitely rewritable. And the read-write power is a little bit higher than other technology, but still it's very small enough. And also, we don't need any the keep power. I mean, for example, DRAM, the memory can be disappeared within 60 microsec. So they should rewrite again when the power is on. So they consume a lot of energy. But this technology, we don't need any extra power except the read-write case. So as you see here, the STT name is quite good. That's why we are working on these synchronous devices. Okay. And okay. Yeah, in other table also said this STT name is quite good compared to other memory. Yeah, but let me say the truth. There are many such tables. Every people who is working on the future memory, there are many kind of memory like PCRAM, RRAM, and there are many new technology. They always have such tables, and they emphasize their technology is good enough. So this is very optimistic cases. So don't believe too much this table, but just you may just keep in mind the STT name is quite good and compared to other technology, but maybe there are something not quite truth. So anyway, the STT name is a good candidate for future memory. And this STT name architecture is something like this. We have a one transistor here. This is a CMOS FET. Field effect transistor. And we have a memory cell here. And we have a bit line. And that means if you have a switch on, the current can be passing through here in this direction or this direction. So with this current, we can write the information in a store layer or free layer. This STM has many benefits because they can be used to any kind of a place. So we call it a universal memory. That means, for example, in this table, we are using DRAM, main memory of the PC, because there are many advantages despite their disadvantage of many things. Because the modern computer architecture, main memory don't need the volatile, non-volatile. Volatile is enough, and they're small and relatively fast. So we are using DRAM for the main memory, but when you store information, you need flash memory. So we need, for example, SRAM for the cache memory. They are large, but the good point is the read-write time is very fast. So we are using SRAM to the cache memory. So there are many kind of memories required for each applications. But STT-MNAME, they are good enough for every application. So that's why we call the universal memory. But in other words, that means they don't have any very strong point. If they have a very strong point compared to other memory, maybe people using MNAME, the STT-MNAME for that purpose. But MNAME has a good performance for in many sense. So people want to using MNAME to many places, but they don't have a strongest point. So that's the weak point of the STT-MNAME. Anyway, so they have a good property of the non-volatile, high scalability, and low power consumption, and good read-write speed, and unlimited endurance. And the density, the cell size can be a little bit larger than the other memory, but still good enough. Okay, so in this sense, in the development of STT-MNAME, there are many issues. Let me summarize these 4 issues. One is called the critical current density, in other words, JC. That means that the minimum current density to switching the cell or writing the information. So they should be low. And the reading signal is related to TMR. And if we have a larger TMR, we have a large sensing margin, and we can read more faster. So large TMR is getting better. And delta, in other words, is called thermal sterility. In every memory, our stored memory can be switched with a long time, because we are talking about the binary memory. If we store the information here, we have an energy barrier. This energy barrier can be overcome by tunneling. There are always finite possibility of this tunneling, and this tunneling can be happens the barrier height divided by kBT. This is the thermal energy. So this ratio, the energy barrier divided by kBT, is defined by delta. So delta should be at least 40 to 60. 40 means the data can be stored 10 years. So usually 40 is good enough for many memories, but for the save, sometimes people require the 60. That means it's lifetime memory. But if the delta is small, that means there are a lot of chance to the information is destroyed. So this is related to the data retention and the size of memory, because the memory size also relates to the energy barrier. Okay, so delta should be 40 to 60 something. And one weaker point is we are sending current to this direction or this direction. So this current should be passed through the insulator layer. So if you're sending too much current or too much voltage, then the junction, insulator junction, can be break down. So that's called the breakdown voltage. It should be large. If it is too small, we cannot switch it. So this means we should make the good MGO barrier. And this is also related to the lifetime of the memory cells and the endurance. So it should be higher. So those three terms are not, we are not talking about this class. We are focused on the critical current density and how we can switch the magnetic layer with the current. Okay, so what is the physics of the STT? Before explain the STT, I'm gonna explain about the angular momentum conservation. So let me turn on some video clips. Just a moment.
By all this time, when it goes off, I spin it back and I stop. With it, I spin. So the question is, why am I spinning? So after the force the new theory law says that every force is an equal and opposite force in the world. So when I push the unit, the needle applying force.
Okay, so I'm gonna show another video clip. Okay, this is another video clip, similar one. Okay, so those two video clips shows the angular momentum conservation. In this video clip, you may remember that one student stand up in a chair, and the other student gave a rotating wheels. And then the student who is standing on the chair, rotating chair, started to rotate. Why that happens? Please answer me. Can you tell me why the student rotate? Anybody can answer? Just a simple answer, please. Yes, that's the key point. This is the angular momentum conservation. Because when the guy is standing up in a rotating chair, the angular momentum is 0. But if the rotating wheel, they have a angular momentum, when they got that angular momentum, the rotating wheel, they want to keep the angular momentum. They want to conserve it. So they start rotating the other way. That's the physics of the spin transfer torque. Okay. So with this spin transfer torque, we can do many things. I'm going to explain it later. Let's move on to the physics of the spin transfer torque. Just a moment. Yeah, here is the concept of the spin transfer torque. If we have a tri-layer, one is the ferromantle layer and the other one is ferromantle layer, and we have a spacer layer. Yeah, actually this is quite similar to the GMR and the TMR structure. So it doesn't matter if the spacer layer is insulator or metallic system. Just think about that one ferromantle layer, which one we call the polarizer. And this ferromantle layer, somehow we fixed it by making it the spin valve system. Or anyway, so let's call this a fixed ferromantle layer or polarizer. And the all conduction electron in this layer is spin polarized to the direction of magnetization. So this electron can pass through the spacer and then see the switching layer. And here the switching layer is not parallel to the polar layer directions. And then as you see here, the blue arrow, blue spin is rotated to the direction of the switching layer. Why? Because of the exchange coupling between these localized electrons, localized spins, and these conduction electrons. So the problem is the incoming angular momentum and outgoing angular momentum, there is some certain difference here. The out angular momentum and the in angular momentum, there is a difference. So the change of the angular momentum implies there is a torque. So when we calculate such torque, we can obtain the red spin direction is somehow rotate to the blue directions. That's the quite similar physics to the angular momentum conservation with the rotating wheel. This conduction electron is rotating wheel, and this localized spins in a switching layer is the student in a rotating chair. So let's back to this slide. And with this, that means we can somehow manipulate the magnetization of the switching layer with the conduction electrons. So with that idea, we can make a magnetization switching, and sometimes you can generate microwave, and sometimes you can move the domain wall. And I'm gonna explain these two topics later. Okay, so let's back to the LLG equation again. And as we already learned, we have a precession torque and the damping torque. And now we have additional torque because of the STT. So today I'm going to explain why this term can be exist and why the torque is something like this. And then with this additional torque, we're going to show what happens in a dynamics of the spins. And we just studied only single spins, but in reality, we need the sum of all spins. That's what we call the micromagnetic study. That is the beyond of our scope in this lecture. Okay, so let's think about the angular momentum again. Okay, so we already know the angular momentum is related, the spin angular momentum is related to the magnetization here. There is some proportional constant. This is called the G factor and Bohr magnetron and H bar. And we already know Bohr magnetron is something here. And this part is gamma, the gyromagnetic ratio. And please remember that Bohr magnetron is gamma h bar of the unit of joule per torque. Sorry, joule per Tesla. Okay. So you can easily imagine that Bohr magnetron multiplied field generates the potential energy. So the unit should be, this is joule, this is the Tesla, and they should be joule per Tesla. Okay. And so we can rewrite this relation to this form. G gamma spin is the magnetic moment. And here the spin angular momentum can be represented by the Pauli matrix. And if this is for the spins, but more generally, the magnetic moment is proportional to the total angular momentum. And this total angular momentum is the sum of the spin and the angular momentum. But in many times, we just ignore the orbital angular momentum because we are playing with the 3D transition metals. That means iron, cobalt, nickel, like that. They are all case, the angular momentum is quenching. They are the angular momentum in a solid, metallic system, 3D metal, they are usually cancelled out or very small. So the contribution for the angular momentum, the orbital angular momentum is very small. But that is not true for the rarest material. Rarest element, this angular momentum contribution is not negligible. So in that case, we should think about the J instead of S. Anyway, so let's think about just M is proportional to spins. And please remember that the unit of the angular momentum is the linear momentum multiplied by distance. So the unit is kilogram meter square per sec. Am I right? And that is nothing else but joule multiplied by sec. Okay, so the h bar, the Planck constant, is also same unit, joule sec. So the other word, the h bar is the unit of the angular momentum. Okay, and the single electron has an angular momentum of h bar over 2 sigma. The sigma is the dimensionless, so the h bar has an angular momentum dimension. So the angular momentum of spin, we have a half of h bar. Okay. So conduction current, that means we talk about the electrons, then they carries the angular momentum due to its spin. And let's think about the total angular momentum of we have several spins, the number of spins multiplied by h bar over 2 sigma. And what's the number of spins in a current? Okay, to make a problem simple, we introduce spin polarization. That means the spin polarization means the number of up spin minus number of down spin divided by the total electrons. So this is the total electrons. So 100, for example, 100% of the spin up means the spin polarization is 1, and 0.5 means the half spin. The number of up spin is how can I say? Anyway, the p value should be less than 1, and large p value means the majority spin number is much larger than the minority spins. So the total electron multiplied by spin polarization, we can say that's the number of spins. So then what's the total number of electrons, this part? Okay, let's introduce the number of electrons per volume, small n. That's the charge carrier density. And the VE is the electron drift velocity. And A is the cross-section of your wire. And delta T is, we are now talking about if you have some wire, and this is area A, and number of electrons this area during delta T. Okay, so this VE delta T implies this distance, and area means this area. So this part is the volume of this cylinder. So when you multiply the number of electron per volume, this generates the total number of electron inside of this volume. And if you multiply the P, that's the number of spin. Okay. And actually, the charge current density is this relation, the NEV. So if you divide by electron charge E, this is the NE, NV. So we can rewrite this form to here. Okay. And the total angular momentum of the spins is, this is the number of spins. This is the number of spins and each spins. So that's the total angular momentum carried by charge carrier density J. So far, is it clear? Do you have any problems to understand this? Okay. The spin polarization, as I said. So if we have a number of electrons, let's say 100 electrons, and if the spin up is 60, spin down is, let's say, 40, then the P value means so this is 0.2. So that means has a different angular momentum. So the sum of two spins, the angular momentum is 0. So only the difference between the spin up, spin down electron can contribute to the angular momentum. So that's why we multiply the P here to the number of electrons. So number of spins is number of electron multiplied by P. Is it okay? Okay. Yeah. So this is the total angular momentum carried by the charge carrier, the current density J. That's the important thing. Or this is the current I. So let's back to this again. So here I said there is some input angular momentum and output angular momentum. That's the J out, J in. So the change of the angular momentum inside of the switching layer can be expressed this form. This is the outgoing angular momentum. This is the incoming angular momentum. So we have to calculate the difference between them. And that happens in the T. And we already know the J out, J in is this angular momentum. Okay. If you have any question during my explanation, please ask the question because this is very important point. Okay. And if we multiply the gamma, you can convert it to a magnetic moment. Okay. And this magnetic moment is a unit vector which only represents the direction of the magnetization, and this. Okay. So the magnetic moment with the you can represent by the spins here. So here J free layer is here. J free layer is here, and we can write the left hand side this relation. Right hand side here we can use this relation. Here this part. So this part are common, and delta is dropped by this term, so we don't need delta t. And the spin S is related to the magnetic moment by the gamma. Okay. So the left hand side is this is the constant. We can send it to right hand side. So dmf dt means the time derivative of the free electron directions. So the free layer magnetization directions. And in the right hand side, we are this is the change of the angular momentum, and here we have to calculate this part. And if we divide these two here, the A is dropped, and df is in a denominator, and ms is also denominator. And now you can easily obtain this prefactor, and the remaining part is this term, this proof. Okay, so let's think about that. This is the direction of the polarization. This is the full layer. I'm sorry, the color of this arrow is opposite to this animation. Anyway, so we have to calculate MF minus M polarizer. And this vector implies this black one, right? But now we are interesting torque acting on the full layer. So that means this torque can be divided by two torque. One is this one, and the other one is this one. And this parallel one to the MF is there is no effect in MF because the parallel torque, if we have a M cross, let's say something, yeah, if they are parallel, there's no effect. So we can ignore this part. And let's calculate only this part. Okay. So we calculate the perpendicular term of this difference. In other words, parallel term is not necessary. So this perpendicular term or this term is, we can calculate something like this. The direction of this torque is this torque is difference between this torque and this torque. So this torque implies M polarization dot MF means the projection of this polarizer vector to this direction. This is this vector. The magnitude of this vector and the direction of MF. So the difference between this torque means this torque and this torque. So so this torque minus this torque, this vector give us this the green one. Okay, I hope the student can follow me. And then this is the inner product of the unit vector, so it should be 1. So we can put this term here. And we know very well known vector identity called the Beckmann rule. I hope every student know this identity. Is it okay? The vector identity called the Beckmann rule. Anyone who don't know about this vector identity? Okay, good. So with this relation, here the MF can be B, and this MF can be A, and polarizer is the C. So you can see this is nothing else but this presentation. So with this Beckmann rule, we can obtain this result. And this one is nothing else but here. Okay. So now we have a torque acting on the free layer by this conduction electron or conduction spins. And that torque can be represented this form. Okay. Here, let me write it down again, this form. Here we play with the unit vector here. All those vectors are unit vector. But if we are talking on play with the magnetic moment, we need extra term here. When you compare to the unit, we have a one magnetic moment and time here, and compared to these two terms equations, we should scale the normalize the divide ms square because we have a 3 m's here. Okay. So this equation or this equation, we can put the LG equation here. So the difference is this term here. And we introduce AJ which one is the prefect of this presentation here, this form, and they are proportional to the current density. That's J, and we put the gamma here. So this term can be represented this form. Okay. And pay your attention, the unit of AJ. Unit of AJ is now we are. Let's check the physical meaning of AJ. Let's start from this part. Yeah. This is the angular momentum per charge. Yeah, please remember that is the angular momentum of the spin. So if we divide by electron charge E, that's the angular momentum per charge. And if we multiply the PJ, means that's the current density and the spin polarization. So that means angular momentum per time and area. Because if you rewrite J to the I over A, means the J can be changed to I over A. And because this current is nothing else but charge divided by time. So this charge, number of charge cancelled out this one. So this representation nothing but angular momentum per time and the area. Okay. And also, in other words, angular momentum has a J sec. So if we divide the sec again, then this is energy. So energy per area. And if you divide dF, the ferromagnetic layer thickness, free layer thickness, then it should be energy per volume. Okay. And if you divide that energy per volume by mu0 ms, so that means AJ is a unit of the field. Because when you multiply mu0 ms, multiply some field, we can obtain energy. This is minus energy per volume. Okay, so the AJ is the field unit, and this m square may be cancelled, two of them. So this is the gamma AJ and m. That's the same unit with the here. Okay. So please remember that this AJ with the inner spin transfer torque, the unit of the field. Okay. So now we back to the energy equation with this spin transfer torque term. We already learned with the external field is here, and the magnetic moment appreciation because of this precession torque. And because of the damping torque, the direction of the damping torque is pointing to the field direction. And what's the direction of this one? Okay. If the MP is this direction, let's say the online is same to the field direction. Then M cross M polarization generate the torque to the radial direction. And then this is the same to this direction. And then we have an cross again, so they generate this direction or this direction. So this term generate torque parallel to the damping or minus damping direction. So that means if we generate large enough torque to this direction, called the anti-damping. Damping is energy passivation process, so they lowered the system energy. But with the STT, they can give energy to the spin, or in other words, they can excite the spin. So if this is large enough, they can switching. So spin torque is larger than damping torque, the switching can be occurred. And if the spin torque is comparable to the damping torque, then the damping torque is cancelled out, then they can precess forever. So we can obtain the stationary precession of the spins. So that can be achieved with the such a spin transfer torque idea. With the magnet field, that cannot be happened. So this STT can open the new way to manipulate the spin direction. That's the very important in any devices. Okay, so let's repeat. This precession torque generate the precession motion, and damping torque generate the damping, and the STT, they can switch from upspin to the downspin. But as you see here, the trajectory is not complex, but somehow they can switch here. Here, if we have a eject here, the magnetic moment can be switched following this trajectory. The green one and red one is quite different. The green one is just a little bit larger than the switching, the critical switching current. Then they generate such kind of long trajectory. But if you apply very large strong current, they can switch very fast. Okay. Anyway, somehow we can switching. Okay. So far, I explained about the spin transfer torque switching. So that concept is very important. So I hope double check the student can understand that part. Do you have any question about this concept of the spin transfer torque? Everybody okay? Okay. So now we understand why this term exists and why this direction. So let's think about that. What is the switching condition? Before going to the switching condition, I'm gonna talk about some resonance theory. The resonance theory means there are many kinds of resonance occur in nature. So in a magnetic system also, the resonance theory is very important. We already learned about the magnetic response, means the susceptibility of the system. We can obtain the susceptibility from the energy equations with the first order linear approximation. This first order linear approximation means we can play with the small disturbance. So after we obtained this susceptibility as a function of the external disturbance, then we can see what happens in the resonance frequencies, and then that resonance frequency spin can absorb the external energy, or in other words, external microwave. So let's think about the susceptibility again. I mentioned the response function in the very beginning of our lecture. That is a very important physical meaning. So most general form of the susceptibility is here. If you have an external disturbance with a field and multiply the susceptibility to the all omega and all q vector, then we can obtain the magnetic momentum or the momentum k and the angular momentum omega. Here, this small omega is the cancelled this with this integral, and this q vector is cancelled out by the sum of this summation, and only k and capital omega is survive after sum and the integral. That's the general form. Okay. And let's assume small perturbation field. That means if we have a strong enough DC field, this is the DC, and can apply the small disturbance, and they are much smaller than the DC term. And as a response, the total magnetic moment must be represented by the sum of the static magnetic moment. This is static one, or stable, and this is the small variation. That means if we have a ground state here, the magnetic moment is, let's say, in this direction. That is the energy minimum direction. Then if you give us some external stimulation, then they can excite. Direction can be changed a little bit. And this vector can be described by sum of these two vectors. So this is the M0, and this is the small m. Okay, here. No. It's not necessary. The H0 and small h can be different direction. Generally, we usually apply this one, small h is perpendicular to the H0, because if you applied h with the parallel to the H0, there's no change. They're already energy minimum point. So this term, actually this small h can be any direction, but this parallel term doesn't change anything. So usually we think about only the perpendicular term. Is it clear? And also same, the magnitude of the antenna field change. So this small m is also generally perpendicular to the M0. That's the general way. And let's introduce susceptibility, which one is for only small disturbance. Okay, now we ignore the M0 part, H0 part. And this small susceptibility is, we call the H susceptibility. Okay, so let's back to the education. Here, we don't think about the spin torque. This is a little bit more complicated. So let's start with the simplest case. Here, the H effective, sorry, we need a vector plot. H effective means all effective, the external magnetic field, and analysis field, and exchange field, and EMAC field, and everything can be represented by the effective field. Please remember that they are nothing else but total energy. Okay. And for the simple case, if we think of just the single spins, we can ignore the many things. But anyway, so let's think about the H effective field. And as we already mentioned, for the first order approximation, let's say the H0 direction is G. This H0 represent the all. I'm sorry, this is it should be effective. Then the direction of the effective field, let's say the G direction, and that means their energy minimum point. And the magnetic moment also, this M is pointing to the G direction. Without disturbance, it's ground state, so everybody happy. And with this external magnetic field, the small external magnetic field, there is some small excitation. That's what we are interested in. And small external field, the external magnetic field and the magnetization are parallel to the z-axis, and only small perturbation field is applied. In this small applied field, as I already said, they are perpendicular to the H0. So they have a x and y component. And the magnitude of H0x, H0y with the frequency omega. And the y direction can have a different phase. So this expression is quite general. They can describe any situation. And because we have a two component xy, the magnetic moment also we have a xy component. The susceptibility must be matrix form. Okay. And if you insert this matrix form to the LG equation, we can obtain this kind of representation. Okay. So it looks a little bit complicated, but I'm going to explain later. This is the actually coupled first order differential equation for mx and my. And we can convert this first order differential equation by combining two of them. We can generate one second order differential equation for the mx and my. Okay. And we can solve this second order differential equation. We can obtain the mx as a function of time and my also a function of time. That's the solution. So with this order differential equation, we can obtain the analytic solution with some approximation. But generally, we can obtain the solution by the numerical way. And that means we can understand the motion of the magnetic moment as a with the external disturbance. That's what we're going to learn. Okay, so this is a good time to stop today's lecture here. And I want to ask to students, please ask me the questions. Yeah, this linear approximation for the susceptibility is very important to understand many related phenomena. So I'm gonna keep going about this in next class. Today I'm gonna stop here. I'm gonna make a break. Please ask questions about today's lecture. That is a good question. Sometimes we are using sign of education is very confusing. Sometimes people using plus sign, sometimes people using minus sign, but it doesn't matter. Actually, how can I say, damping should be decreased of the system energy. So when you set up the equation, direction of damping should be this direction. So if you have a appreciation of this direction, then let's see here, the dmdt in a top view, if you have a precision here, dmdt is this direction. Okay. And m cross dmdt means now m is somehow this direction. So m cross dmdt is this direction. So alpha should be positive, plus alpha, something like this. But in some case, people make the different sign here. Then they have a positive direction precession. Then it should be minus sign here. Okay. So I'm sorry, but sometimes I'm didn't pay too much attention to keep the sign of the alpha in front of the damping term, but yeah, then may be some mistake. Oh, okay. So talk, this term represent actually same to the this direction or this direction depends on the sign of AJ. Means if you're sending current to this, let's say here, I said that we can send current to this direction or this direction. So in one direction, from the this case, we can switching this layer to the polarizer direction. But if you're sending current the other way, then the switch layer can be switching to opposite direction to the polarizer. So in this case, switching can be occur this direction or this direction depends on the current direction. Okay, so we can switching free layer to parallel to the polarizer layer or anti-parallel to the polarizer layer depends on the current direction. Is it okay, Theo? Or your question is about the direction of this term? Any other questions? Okay, this vector product means, let's simply say this is the MP and this is M3. Then this term generate this direction vector, right? And this term, if you multiply the M again, then we have a this direction. right? So, yeah, so this term implies the m cross something. So that means the result vector should be perpendicular to the m itself, right? So if we have one vector and they have a possible perpendicular direction is only two. One is this direction and the other one is this direction. And this m cross m polarizer can generate this torque. So finally we have this or this term. Yeah, this is the we need a three-dimensional thing, so it's not easy to explain with this board, the slideshow with the right. Yeah, we need some hand waving explanation in this case. Sorry about that. But you can do it by yourself. So, next question is about this part. Okay. So we can apply the external magnetic field, the small external magnetic field. They should be perpendicular to the z direction. So we have only x and y component. And if we apply the same frequency, we have such terms. But if we apply the different phase to the y direction, we have a finite phase difference. They can be simply zero or it depends on, means if this is zero, we have a, let's say, the linear polarization of the H vector. Depends on this magnitude. So into this xy, they have a such oscillations. If we have a finite value of the phi, for example, phi over 2, then the vector H vector is something like this. Depends on the time the field is rotating. And if we have a different phase, let's say like this, then this is more complex. It's kind of a elliptical one. So in a time scale, this term is something like this. HY is the little bit different. So they can be combined. This is for the general expression. After you calculate, you can put this number, specific number, then you can obtain automatically all response. Is it okay? Any other questions? Okay, if you no more questions, let me finish this lecture and see you Wednesday. Okay, bye.